Okay, the topic of the day is continuity. So this is our next, this is kind of where we head from limits. So real quick, why don't you guys, I know we haven't talked about continuity, but I bet you can make a pretty good educated guess. Discuss the continuity of this function. Absolute value of x minus 2 over x minus 2. What do you think? What's that going to look like? No. It's not a vertical asymptote. There's a couple ways we could go about. First of all, in your mind, you need to get a sketch in your mind of what this is like, right? Anybody want to hazard a guess what this thing looks like? Okay, it's going to be a step function. Good, so it's going to look like that, right? Where's the what's the height of the step function going to be? Like the top horizontal line is at what y value? 1, bottom one? At what? Negative 1. Okay, where is it? Where's the break in the step function? At 2. Yeah. How do you know that? There's a couple ways you could do this pretty quickly. Right, here's one way you could do. That's what it looks like, right? Okay, how? How do you know that? Well, one way is this way. Think about this. Like if we write if we make that f of x, isn't that the step function? Isn't that this step function? Agreed? Okay, so that's not what we have though. What we have is this one. What we have is absolute value of x minus 2 over x minus 2. So what is that? If f of x is absolute value of x over x, this is f of what? F of x minus 2, isn't it? Everybody see that? Right? Because the green function says whatever I'm putting in for f, I'm taking its absolute value in the numerator, and it is represented without an absolute value in the denominator. So if that thing is an x minus 2, then isn't this just an f of x minus 2? Okay, so then how is the graph of f of, just in general, without referring to any specific graph, f of x minus 2 is transformed how from f of x? Right 2. Exactly. If I subtract 2 from the input variable, that moves it to the right by 2. That's part of our transformations of functions, right? So that's probably the easiest way to just come up with in your brain with real quick. That's what this thing has to look like, because it's just been translated 2 to the right. Okay, another way you could do it is you could do it the way we talked about in class, last week. If we know that the absolute value of a is defined as a whenever a is positive and the opposite of a when a is negative, then we know that the absolute value of x minus 2 is going to be positive whenever x minus 2 is positive. And when is x minus 2 positive? Well, when x is greater than 2, right? And it's the opposite of x minus 2 whenever x is negative, which is when x is less than 2. And so then we could take this piecewise function and we could just divide each part of it by x minus 2 to come up with our function, right? Everybody see that? If we're trying to see what the graph of this thing looks like, we would start with the complicated part, which is the piecewise function for the numerator. And then whatever that piecewise function is, we just want to divide each piece by x minus 2, right? Anybody get that? Do you see why we have to, it has to look like a piecewise function though, because the absolute value part of that function is defined as a piecewise function. So therefore we have to treat the whole thing like a piecewise function. Anybody see that? Okay. So then what would that look like? Well, if we just took all of these parts and divided each of those parts by x minus 2, wouldn't we just get that? Right? And what is that? Well, x minus 2 divided by x minus 2 is 1. Negative the quantity x minus 2 divided by x minus 2 is negative 1. So sure enough, we get exactly the function you guys described, and we got it with a break where you told me it was going to be, at 2. That's the break in the function. Either way, that way's a lot easier, quicker. Okay? But now that we've got the graph, discuss the continuity. What do you think? We haven't even used these words yet, but just make an educated guess here. Do you think that that red function is discontinuous? Yeah, where? At 2, right. Okay, how come? Here's a good working definition of continuity. A function, and we talked about this a couple years ago in Algebra 2. A function is continuous wherever I can graph the function without picking my pen off the board. Anytime I have to pick my pen off the board for any interval, no matter how small, that constitutes a discontinuity, right? So there is a discontinuity here at 2. All right. So let's talk more rigorously about continuity. So we've got our informal definition. Now let's come up with a formal definition. Okay, so in order for a function f of x to be continuous at a point A, it has to meet 3 conditions. If you can check off these 3 conditions, if you meet all 3 of these criteria, then it is continuous at that point. The first one is that it has to be defined at that point. The function has to be defined at that point. So there's the first criterion. F of A is defined. Okay, what does that mean in terms of an ant? It can stand there. Yeah. The ant has a place to step at x equals a. He's standing on solid ground. Okay, the second part. Not only is the function defined, the limit exists as x approaches a. So what does that mean in terms of an ant? Okay, it can't be approaching, it has to approach the same point from 2 different directions. And there is a single place then where the ant anticipates stepping. Okay, ants approaching x equals a from either direction anticipate stepping on the same place. And then what do you suppose has to be true about those first 2 criteria if the function is going to be continuous? The ant has to have a place to step. He has to anticipate stepping on a place. And what do you think, Sophia? Say it again. There you go. So those things have to agree, right? The limit of the function as x approaches a has to equal the value of the function, which of course means the ant's always going to step where he anticipates stepping. Okay? That's it. Those are if we meet those 3 criteria, then you know, guaranteed, that f of x is continuous at that point A. Okay, let's look at some examples and kind of talk about, apply this. Apply these criteria to some specific examples. Before we jump to the next page, though, a function is discontinuous at a point A if it fails to meet any of those 3 criteria. Okay. If you fail to meet either of the first 2, would you agree that obviously the third one fails? The third one depends on the first 2 existing, right? Okay. Okay, so let's try, is that the next page? Yeah. Let's try this guy. Okay. So let's discuss the continuity of this function. The function is f of x equals x squared where x is not equal to 1. So let's look at this in terms of our 3 tests. And we'll just go through and check them. So do we meet criterion 1? Thumbs up or down? And what's the point we're considering here, do you suppose? 1, yeah. We meet criterion 1, the answer is no, we do not, do we? The function is not defined. And so therefore we know automatically that we're going to fail criterion 3. Do we meet criterion 2? Up or down? Yeah, what is the value of the limit of f of x as x approaches 1? It's 1, yeah. So that one, we actually do pass that criterion, but we didn't pass all 3, so the function is discontinuous there. Does that meet with our informal definition, match with our informal definition? Yeah, right, it does. Because if I were going to graph this thing on the board, I would have to pick my pen off the board to skip that one point that constitutes the whole, right? Everybody see that? Okay, give me thumbs. How are we doing? Okay. How about this one? What is that function? What does that mean again? Greatest integer function. Yeah, yeah. So another way of writing that, that's the greatest integer function. Another way of writing that is a floor function, like that. So it's always right. It outputs the greatest integer less than or equal to the input, right? So then we know what that looks like. It looks like that, doesn't it? Remember talking about this one? Okay. So what could you tell me about this one? Discuss the continuity. Well, let's take the criteria one at a time. Where would be the points of interest for this function? Like what are the points that are a little weird that we want to investigate? How would you describe all? There's an infinite set, but what are they? Okay, integers, right? Not just whole numbers, because they could be negative also, right? So we're looking at the set of all integers. So is this function defined for all integers, for the set of all integers? Thumbs up or down? It is, right? There's no place that the ant can't stand. On every integer, he has a place to stand, right? So, check. For the set of integers, does the limit of this function exist as x approaches any arbitrary integer? No. How come? Okay, because I'm getting different values from the left and the right. Yeah, okay, so we fail that one. If we fail any of these, we fail the third. And so we would say, no, this function is discontinuous at every integer. Okay? F of x is discontinuous at all x that are elements of the set of integers, right? So all integers. Okay, and how come? Because the limit doesn't exist. Okay? Let's try another one.
What does the Z stand for?
Capital Z is just normally the set of all integers. Yeah. Okay, what about that one? Based on the graph. Okay, so we're interested at the point 1, right? Okay, so vote with your thumbs. Is f of 1 defined? Sure, it is. Is the limit of f of x as x approaches 1 defined? Yes. So we good? What's the issue?
They're not equal.
They don't agree, so it fails the third test. And what's the consequence of the third test? That's the consequence. If the ant doesn't anticipate stepping where he actually steps, right? So again, it's pretty obvious I would have to pick my pen off the paper to draw this thing, and so it is discontinuous at 1. Okay? Okay? Because the limit doesn't agree with the function. All right, let's look at one like this. This is the kind you're going to see on your homework. Okay? So I gave you a graph. Here's the graph. So and they remind you about the 3 criteria. Now they want you to pick what are the values of A where is the function discontinuous? First thing they ask, where is this function discontinuous? Just using your Penn model. At what places?
3 and 4.
At where again?
3.
3 and 4. Anyplace else?
2.
2.
Oh.
Why 2?
It's
Right, because I have to pick my pen off the board because I can't ever get to infinity. So in order to get from the left leg of that infinite spike to the right leg, I'm going to have to pick my pen off the board because otherwise I have to go to infinity, which I can't do, right? So it is discontinuous there because it's a vertical asymptote. So we get 3 places, 2, 3, and 4, where the function is discontinuous. Okay, now, they want you to determine, of those 3 discontinuities, the points at x equals which values violate the first condition. The first condition is the function is defined. So in other words, we need to know where is the function undefined. Let's vote with our thumbs here. How about 2? Is the function defined or undefined? Undefined. So 2 needs to be one of those, right? What about at 3? Is the function defined? It is. Okay, so we're okay there. That does not fail the first test. What about at 4? It's undefined, right? So the points at 2 and 4 violate the first test, or the first condition. Everybody get that? Okay. How about the second condition? Which of those points 2, 3, and 4 violate the second condition? Which of them do not have limits? 2 and 3. Everybody see that? Okay. You might say, well, 2 does. What's the limit of the function at 2? Infinity, but infinity is not a number, right? The function, the limit has to have a finite value for it to be defined, okay? I read your mind. I could see that. Okay, and therefore the third condition is violated where? All of them, right? Because at least one of those places, 2, 3, and 4, violates criterion 2 or criterion 1. And so if a value of x fails either one of those, 3 can't apply, right? So that would have to be all 3. Okay. Make sense? You all prepared to answer those now? Good. Okay. So you think, huh? Let's try that one. Let's try that one. So a is -7. Determine whether the function is continuous at a. Use the continuity checklist to justify your answer. First of all, is it continuous at -7? No. Guaranteed it's not. How do you know immediately that it's not? Because it's a 0 of the bottom, right? So it has to be a value that's eliminated from the domain, excluded from the domain. Okay, but we don't know yet why, what's going on. How are we going to find out?
Solving it. Yeah, solving it. Resolve it.
What do you mean resolve what?
The indeterminacy
Of what?
of the limit.
Of the limit. Okay, right. Okay, so we already know the function doesn't exist at 7. So it failed test 1. We can't plug it in, but what we could do, we need to evaluate the limit because we don't know about test 2 yet, correct? Okay. So we already know one thing. We know select all that apply here. What are we trying to do here? Justify your answer. So it's going to be
We know B. Has to be B.
so like we know. Okay, I see what they're doing. Yeah. So that's not an option because it is discontinuous there. Right. Okay. We need to find the limit though. So let's do this limit. This is really good practice. If I try to evaluate this directly, what do I get? Because I should just try. If I try it and I get 0 on the bottom and a number on the top, we're done, right? Then we know this is a vertical asymptote and we don't really have to go any further. Okay, but that's not what happens, is it? If we plug this in, we're going to get 4 times 49 is what? 396. Hold it. 4 times, no, 196, right? And plus 15. Is that? Are we going to get 0 over 0? Yeah, we do. We do. Right, we do. We get 196 plus 15. So we're getting 211. And then if we plug in -7 here, did I do that wrong? 49.
It'd be -1.
I factored it. I don't know if that's what.
-119.
Negative 139, right? Or no, you're right, 119. How is this not working though? Did I write this down wrong?
You get 92 on the top.
Oh, okay. So it doesn't end up being 0 over 0, right? Okay, good. So we're doing it right. I was doing it right. So I was thinking it was supposed to be 0 over 0. I couldn't figure out how that was going to work. So what do we know about this then?
It's
We already know pretty much everything we need to know here.
it's a vertical.
So it's a vertical asymptote, right? And so what do we know about this? Which of these are going to apply? The first one obviously does not apply. Does B apply? The function is not continuous at -7 because f of -7 is undefined. Yeah, that's true. The function is not continuous at -7 because the limit does not exist. That's true, right? Why doesn't the limit exist? Because when we evaluate the limit directly, what did we get? We got some number, which was what, 92 you said? 92 over 0, which means vertical asymptote, right? No limit, okay? Question? Okay. So the function is not continuous because the limit doesn't agree with the function. Well, obviously that one, that's a freebie, right? If either B or C was checked, D had to be. That's the third test, right? Everybody see that? Okay. Did we really need to factor this thing? We didn't really need to, right? If we factored it, were any factors going to cancel? Was the factor x plus 7 going to cancel? No, it wasn't going to, right? Because we did not resolve the indeterminate. Well, we didn't have indeterminacy to resolve. Okay. Does that factor easily, the top one? This will.
It's x plus 3 times 4x plus 5.
Okay, how could you factor that one really fast?
I did I put the 4 to the 60.
That's how you do it, yeah. So 4, right, so we just want to know, can I split that middle term and factor by grouping? Right, this is good practice. You guys got to get really good at mental math. You're going to do so much algebra this year. So 4 times 15 is 60. So we got to see, are there numbers that multiply to 60 and add to 17? 12 and 5. So then we know right away, we would just split this guy. We're going to split this guy into 12x plus 5x, either one, doesn't matter, right? Doesn't matter the order. And we would do just a quick review of this stuff. And then we'll just factor that by grouping, and that's really easy to do, and we get an answer fast. What would I factor out of the first two terms? What's left over?
X plus 3.
So what do we know has to be in the second one? X plus 3. And what do I factor out to make that happen? So would you agree then that this thing factors into 4x plus 5 times x plus 3? Okay, good. Okay, types of discontinuity. So we understand the criteria, what point discontinuity means, or continuity at a point. We know the three criteria. We know visually what it looks like. Now let's kind of break down the different types of discontinuities that we could see. So you could see a point discontinuity. Here's an example of a point discontinuity. Point's missing. What's another type of point discontinuity? What else could I draw that's a point discontinuity? Okay, so like this, that's not a point discontinuity because more than a single point has been dislocated. What do you think? Yeah, okay, this. Is this what you're describing? Like that, right? Those are point discontinuities because only a single point has been moved or removed, right? Okay, what do you think a jump discontinuity is? Yeah. The ant has to jump, right, to span that gap, okay? And then an infinite discontinuity would be what? Either they're both going up or they're both going down or they're doing that, right? It's a vertical asymptote, okay? Okay, so now we can characterize, there's a real important distinction. Would you agree that both of these are macroscopic discontinuities? In order to repair these discontinuities, how many points would I have to move on the function? No. In fact, how many? An infinite number, right? I would have to repair the jump or the infinite discontinuities, I would have to move an infinite number of points to connect those.
Even for the first one?
No, not for the first one. For these two, right? So for these two. But for the first two examples, right, those, I only have to change the value of a single point and I fix it, right? So therefore, we say that these types of continuities where only a single point is involved, we call those removable discontinuities because they're so easy to remove. All we have to do is just redefine the value of the function at one point and we're done. These other types are non-removable discontinuities because in order to repair those, I have to change the entire function. I can't just redefine the value at one point, okay? So then we have removable versus non-removable, okay? And just for your notes, and this is just stuff right out of the text, okay? Notice that removable discontinuities can be repaired by adding or moving a single point. Non-removable requires that we move an infinite number of points. So removable, non-removable, okay? Just for your notes. What am I doing with this? I don't know, it's up there twice, don't know why. Okay, so discuss this continuity. Let's go through the checklist. We don't have a graph to look at yet. We're not going to have a graph. Let's not do this with a graph. Thumbs up or down on test 1. Yeah, I'm seeing thumbs up. How come? Okay, yeah, so the ant always has a place to stand, right? For every value of x, the ant is standing on one of those two pieces, right? So check. Test 2. We don't know yet, right? How are we going to find out? I'm seeing some thumbs down. Why thumbs down? Well, do we know that? We haven't tried it yet, have we? Okay, let's try this. So let's see what happens from the left. The limit of f of x as x approaches, what's the value in question? 2. As x approaches 2 from the left is the limit of 2x as x approaches 2 from the left, which is what? 4. So the limit from the left is 4. the limit of our function as x approaches 2 from the right would put us on the bottom piece, right? It'd be the limit of the bottom expression. What's the limit of x squared plus 1 as x approaches 2 from the right? 5. So does the limit exist? Thumbs up or down? Thumbs down. Does not. Okay, makes sense? And so, say it again. Question? You good?
They're not equal.
They're not equal because limit from the left and limit from the right are different. So what's that telling us about, I bet you can tell me what kind of discontinuity this is.
Jump.
It's a jump discontinuity, right? Because the ant's going to have to jump over some gap to get from the left piece to the right piece. So test 3, up or down? Fails. Okay, and what's our picture? How'd we do? So yeah, we're right. We have a jump discontinuity, so it fails at 2. Okay. How about this one? Does it pass 1? It does. Yeah, it does. Okay. How about test 2? Does the limit exist as x approaches 1? Okay, how would I find that? Let's do that one. So the limit of f of x as x approaches 1, not 2, sorry. As x approaches 1 is the limit of what? Limit x squared, right? Because when we're approaching 1, for every value other than 1 itself, the function is x squared, right? So we're taking the limit of x squared as x approaches 1, and what is that value? 1, okay? So the limit does exist. How about test 3? Fails. You're right, because what is the value, and here's why. What is f of 1? Aha, value of the function does not equal the value of the limit. So we fail the third test, and what's this one going to look like? It's 1 point that's been removed, that's been picked up off the function above or below, right? In this case, it's above. So we get that, right? Okay, how about this one? Write a piecewise function that makes f of x everywhere continuous. Okay, where is this function discontinuous? At what x value? At 0, okay. So I need to, the function is discontinuous at 0, so I need to write a piecewise function that defines a value at 0 then, right? Because that's where we have a gap in this thing. Okay, so every place other than 0, so I can just say x is not equal to 0, what's the definition of the function every place other than 0? No? What is it? Sine x? Sine x over x, yeah, it's that, right? That's the function. But what's the problem we started with? Well, this function that we originally started with, I should call this g of x, not f of x, because we've changed it. This is f of x, right? So f of x, I can graph it every place except x cannot equal 0 in f of x, because I have a 0 on the bottom then, right? So my piecewise function is going to be sine x over x everywhere except 0. So what's happening at 0? Yeah. Right? The value of the function needs to be equal to what the limit would be of the top piece if I approach to 0. Okay, so you guys, you know that answer. The limit of sine x over x as x approaches 0 is what? 1. So that needs to be the value we define then at x equals 0 to fill in that hole. Everybody see that? What we did? Okay, so our piecewise function is continuous because we filled in that removable discontinuity. Give me thumbs. Okay? Yikes. What about this one? Okay, you guys hate these compositions. Okay, I'm going to show you why these things are no big deal. Like this is I'm going to make this so easy for you. It's really, when you try to think about this as two discrete functions, I get that then it's kind of cumbersome, right? But don't. How would I write this as a single function? As just one composition that looks like a single function, not in two pieces. If I want to do f of g of x, we're doing g of f of x, I guess, right? So what is that? Well, what's g of x? G of x is this. What does that mean? G of hand would just be the cube root of hand plus 11 over hand plus 4, right? Agreed? So g of f of x is going to be what? Cube root of, okay, whatever f of x is, which is this, right? Plus 11 over on the bottom, what am I adding to 4? X squared minus 4, f of x, right? Well, that's pretty easy to simplify. What's that give us? What do I get on the top? Cube root of x squared plus 7. On the bottom. Okay. So is g of f of x continuous at x equals 0? No, it's not. That's why. Okay. I mean, we could break this into pieces. Is f of x continuous at 0? I think it is. Look at f of x. What's the value of f of x at 0? Negative 4. Yeah, it is, right? Is g of x continuous at x equals 0? Yeah, it's fine, right? Is g of f of x continuous at x equals 0? No, it is not. And why is that? Okay, there's a reason for that, and here's the technical reason. It's because g of f of 0 is equal to g of f of 0. What is f of 0? F of 0, you could have told me, is negative 4, right? G of negative 4 is a problem, right? So the output of the interior function becomes the input of the outside function, and that caused an issue. But again, that seems complicated, doesn't it? Does that? No. So just simplify the function and see, right? It's pretty easy to calculate what g of f of x is, right? Just by simplifying whatever you get. When I plug x squared minus 4 in for x, and then that function, it's really easy to see that 0 is disallowed because it gives us a 0 in the denominator. That's the easiest approach for those kind, okay? All right, I bet you we're getting to... Yeah, that's a good place to stop. Okay? Is that enough for one day? I don't know.
Yeah.
Enough? Okay.